and co-founder of the Livermore Lab Foundation. Welcome to Summer Slam Special Edition. Several things make this event special. First, it showcases Livermore's top summer student interns. These selected students from a large intern population will have the opportunity to receive individual science communications coaching from Amy Ains. Amy is the co-author of Championing Science and founder of Talking STEM. This event is special because it's made available to lab retirees and members of the LLLRA and the community. As a lab retiree myself, I sometimes miss the thrill of engaging in day-to-day scientific discussions, and I'm always looking for ways to connect. So the Livermore Lab Foundation is pleased to showcase these students and their summer research to you. Not only does the foundation hope to advance science and inspire next generation scientists, but we also like to provide an additional link between the lab and the community where it makes sense. With that, I'll turn it over to Sally Allen, the Executive Director of the Livermore Lab Foundation, to go over today's agenda and to provide you with a brief overview of the foundation. Thank you for coming and welcome.
Thank you, Donna, and welcome to everyone. We're so pleased that you could join us today to hear from this impressive group of students. I wanted to take just a few minutes to discuss today's event and to share a little more about the Livermore Lab Foundation before we turn things over to our student presenters. Here is a quick look at our agenda. This is the second annual virtual Summer Slam Special Edition, although the foundation has been partnering with the lab since 2018 to help recognize and honor the annual summer poster research presenters. This year, the lab hosted over 600 summer research students across all of the programs and directorates. And about a third of those students participated in the lab's virtual summer poster sessions just last week. The students that you're going to meet today were selected by their mentors and senior leaders for their exceptional work and presentations, showcasing the depth and breadth of the world-class science and technology at Lawrence Livermore National Lab. We've allotted approximately 5 minutes for each project, including some Q&A, and have left some room at the end for additional comments or questions. More on that in just a minute. So most of you are hopefully aware of the Livermore Lab Foundation, but you may not know as much about what we've been up to over the last 5 years since our inception. As Donna noted, we're an independent nonprofit organization dedicated to advancing scientific knowledge, research, and inspiring future STEM leaders. Our focus is to harness the power and promise of the science and innovation at Livermore Lab for the greater good. As a 501c3 organization, we enable opportunities for the lab to engage in new ways with philanthropy, academia, industry, and the community to help address some of society's greatest challenges. As you know, the lab's multidisciplinary approach and commitment to team science makes it uniquely positioned to address critical issues in energy, climate resilience, biosecurity, healthcare, and so much more. The foundation has provided funding for groundbreaking research in 2 key areas, climate science and advanced healthcare. We're working with the lab's Carbon Initiative team and others to help advance public understanding of the science behind technologies like carbon capture and storage and to help inform the policy and community decisions needed to help California achieve its goals for carbon neutrality. In healthcare, we provided early stage funding for several projects that are leveraging the lab's unique capabilities in computing, engineering, and the biosciences to help us better understand, diagnose, and treat rare diseases such as ALS and other neurodegenerative disease. Advancing science for the greater good also requires that we continue to bring new people and perspectives to the lab and to STEM disciplines. And in the lab, the foundation seeks to do this every year through our STEM programming and opportunities. Before you hopefully are seeing just a snapshot of the 2021 STEM programs that we are offering, all designed to engage young people who might not otherwise have access to the lab and provide meaningful connections through mentorships and hopefully inspire them to pursue future educational and professional opportunities in STEM disciplines. Every STEM program that we support would not be possible without the incredible leadership and dedication from champions inside the lab. And I want to take a moment just to acknowledge and to thank Joanna Albala, who's with us today, for all that she has done to support science education and the students both at the lab and in the community. So thank you, Joanna, for being here. Which brings me back to today's program and a few ground rules. By now, you're likely all experts in Zoom webinar protocols, but just in case, here are a few. Everyone on today's Zoom will be muted except for our presenters. And we will be trying to spotlight each speaker as they're speaking to their particular project. We would encourage you to use the Q&A function at the bottom of your screen to submit any questions or comments, or just to cheer on our students as they're speaking. We welcome that. And we will do our best to address at least one, if not two questions immediately following their presentation. And again, have some time at the end for additional questions. Finally, we are recording today's event, and we look forward to posting it on the Foundation's YouTube channel in a couple of days, and we will follow up to send you the link for that. So that's it from the Foundation's perspective. With that, I'm really pleased to hand the agenda over to our students, who you came to hear today. And I'm happy to introduce our very first student, Sarah, who some of you may recognize from last year's SummerSlam Special Edition. Welcome back, Sarah, and take it away.
Thank you. So I'm just gonna start off. So, good morning, everybody. My name is Sarah Azar. This is, like she said, my second summer interning at NIF. And right now I'm an undergraduate senior at the Georgia Institute of Technology studying mechanical engineering and nuclear energy. So today I'm going to talk to you about investigating laser-driven radiography with Monte Carlo knife edge simulations. So to start, I'm sure everyone here has probably taken a photo at least once in their life, but maybe not everyone has taken a photo using high energy X-ray photons, and probably even fewer people have done so using X-ray photons generated with lasers. But the rules of taking photos are kind of the same no matter what the photon energy is. Here we have three metrics that make a good photo that you take with your normal camera. You want high resolution, good lighting, and the correct shutter speed. There's analogous features for radiographs taken with high energy X-rays, which include high resolution, high energy photons, and short pulses. A radiograph is just an image taken with high energy X-rays rather than low energy visible light photons. So radiographs tend to look something like this. Photo A is a CAD model of the actual object that was radiographed, and photos B and C are two different radiographs of that object. You might notice that photos B and C have different resolutions, which is indicated by the blurring around the edges. Resolution is a first step into improving radiography because it allows us to take more accurate photos. So my project was about finding out which parameters that go into a radiograph will improve resolution the most. And to start with this, I was running simulations on laser-driven X-ray generation at the lab. So the way that the lab generates high energy X-rays is by using short pulse lasers and firing them into a target of some high Z element. And when these electrons hit the target, the process of bremsstrahlung radiation occurs, which just releases photons. And these photons are on the energy level of X-rays and are what we want to use for radiography. So here I've shown the simulation setup, and I did my simulations in the CERN program GAMP4. In blue is the electron generation hitting the target in gray. And the way it generates X-rays looks something like this, with the electrons in yellow and the X-rays in purple. And what I did in my simulations is place a knife edge, which is shown here in red, in front of the detector. So because this blocks out some of the X-rays that would be used to take the radiograph, it actually creates a shadow on the detector. And we know the geometry of the knife edge is to be very sharp. So when we get the resulting radiographs, we can look at any decreases in sharpness, and from that determine blurring and resolution. So by testing different input parameters, we can see how the blurring over the knife edge changes. Here I've shown two pretty extreme results. One where the input parameters were a large angle of electron emission and a small area over which the electrons were generated, and one with the opposite with large angles and small radius. So this is what the results look like. And the blue line here shows the intensity of the X-rays that generate the radiograph. And the red line shows the gradient of this that was fit to a Gaussian. And the gradient is essentially just the first derivative and shows the amount of blurring that occurs on each point in the blue line. And as we can see here, the results show that the source diameter or source radius is a larger impact on the final blurring than the angle. So from this, we can use these results to provide information for real experiments being done at NIF. So with these results, we could say we're only going to test things with a large and small source radius versus varying angle that much because it doesn't have that much effect on final resolution. Thank you.
Thank you so much, Sarah. Great presentation. As we said, you were here last summer. How did this compare to what you did last year? And how did you select this work to focus on?
Yeah, so last year I was still working in the context of radiography, but I was doing something different in that I was building a model that provides more information about the X-ray spectrum versus what I'm doing now, which is comparing different parameters that go into the spectrum. But one really cool thing for me is last summer, I wasn't running simulations. I was using my mentor's data and building models. And this year I got to actually run my own simulations via the lab supercomputer. So that was super cool for me.
Oh, very cool. Good to hear it. We have a question from the audience. They wanted to know what will change as a result of higher resolution radiographs.
So my understanding is that our radiographs are used to take photos of implosions and other HED or high energy density science applications at the lab. So because these implosions at NIF, the radii we get ends up being microns long. So we need very high resolutions to be able to even differentiate small differences because we're not taking, a normal photo of a person. We're taking something orders of magnitude smaller.
Mm-hmm. Great. Thank you so much for your presentation. Great job. We're going to move on to our next speaker. We have Aaron, and I'm going to share our screen so we can have Aaron next. Aaron, you are on.
Excellent. Can everyone hear me?
I can.
Excellent. Yes, my name is Aaron Barrett. I am a third-year graduate student at the University of Kansas in mathematics. And my presentation is command verification through matrix completion. Next slide, please. The transition to widespread use of renewable energy resources has become an issue of long-term societal stability, international policy, and even economical strategy. As limitations in the design and manufacture of these technologies are surmounted, practical considerations become a primary issue when incorporating these resources at a large scale. Currently, utility companies limit the number of solar inverters installed in both residential and commercial power systems. And the limiting factor is twofold. Solar inverters place power back into the system as opposed to simply taking it, and these inverters are smart. They're essentially small computers capable of processing basic commands and ultimately present a new vulnerability into the wider network. So to address this, we need to make use of these computing capabilities to mitigate both unreliable devices and bad actors. Next slide, please. In our case, we want to determine if there's an overvoltage scenario to warrant a command to change the state of the grid. Could we maybe go back and then forward? Thank you. Mm-hmm. So by exchanging this information over time, we actually create a data matrix with the corresponding meter voltages. And we use optimization to generate a model at each inverter to predict these the meter voltages, which is what we need for command verification. So we apply ridge regression as a learning step in order to generate a set of weights. So we can determine an accurate meter voltage using a linear combination of solar inverter data. And that's what we see with these dot products. And specifically, we want to apply this model even when these devices go offline, so we have these missing components, and which means we can't apply these weights in this dot product. So to address this problem, we apply matrix completion using this learning data to propagate the missing voltages in time so that we can apply these weights. So in short, matrix completion is a rank minimization problem on the expanded data matrix, and this uses convex relaxation to recover the missing entries while enforcing the information that we know. That's this constraint equation here on the bottom. So this approach uses the correlation between known voltages to predict the missing ones, but it doesn't necessarily mean this is accurate enough to apply these weights. Next slide, please. So to study the efficacy of this approach, we applied this technique to an RPU model that is comprised of 364 solar inverters that we can use. So we enforced that 10 of them go offline for a day, and we still want to determine if there's an overvoltage scenario. So we already know that applying these weights with no missing information, in fact, gives a good meter voltage. And these are the black dots and red triangles respectively. And specifically, this gives a good estimation near this overvoltage threshold, which is what we care about. So for our contribution, we look to the red line, where we can see that this completed data still gives a rather useful meter voltage estimate, specifically near this threshold, typically within a few volts, which according to our scale is quite good. So to conclude, matrix completion allows us to apply the learning step in the scenario where a reasonable subset of inverters go offline, as well as the learning step itself. And thank you all for listening.
Great. Thank you so much, Aaron, for your presentation. We have a question from the audience. They'd like to know, Tom Adams would like to know, do the simulations take very long to run? And can you make enough runs to explore more parameter changes?
Yeah, so in the co-simulation framework, this is like kind of outside of my project, but in terms of like the co-simulation framework itself that was already there, we used time dilation to kind of speed that up. So running like a full day simulation is only about 12 minutes, but to run like this optimization on like my local computer really only takes about probably 3 to 4 minutes for the entire day, maybe 5 if we're being generous. So it's actually pretty efficient even on like a regular quad core laptop. So what we would do next is actually explore maybe even corrupted data where there's more noise than just from sensors in the data matrix itself, and maybe a less stiff model because this model's pretty friendly, let's say.
Super, thank you. Another question was whether the lab is partnered with industry to implement any of this work.
Yeah, I believe that's what this project is. And if I'm not mistaken, these are smart inverters that we're assuming. And the data that I use is coming from those inverters. It's just not in the co-simulation framework itself. It was, I guess, more on the data analysis side, you might say.
Super. I think Tom has a follow-up question. I'm unfortunately going to have to move us along, but maybe you can answer his additional questions in the Q&A, Aaron.
Sure, I'd be happy to. Thanks again.
Super, thank you so much. Okay, our next presenter is Kirona. Kirona, you're up. Thanks for being here.
Hi. Thank you. So I'm Kirona Bergstrom. I am a PhD student in the Applied Math department at the University of Colorado, Denver. And my project is on learning nuclear reaction theory with GIN. Next slide. The chart in the center of this slide is the chart of nuclei. There are over 3,500 known isotopes represented in this chart, and each of them is involved in multiple different interesting nuclear reactions. If we start at the lower left corner of the chart, we have our lightest nuclei. Some of these are involved in fusion reactions inside the sun. As we move up and to the right along the chart, we get to elements that are heavier than iron. Some of these are created in the rapid neutron capture process in supernovae. These applications can tell us about the origins and abundances of elements in the universe. As we get to the upper right corner of the chart, we get to the heaviest known isotopes. Some of these are involved in fission reactions powering nuclear energy here on Earth. Simulating these kinds of large-scale applications requires good theoretical models for the underlying nuclear reactions that drive them. Next slide. Nuclear reaction models need to be able to predict important quantities such as cross-sections, which are related to reaction rates for various nuclear reactions. The plot on the left of this slide is a cross-section prediction for a realization of a parameterized theoretical model for a neutron capture reaction. Now, these theoretical models are often quite complex. So for example, the statistical reaction Hauser-Fishbach model requires 14 or more parameters to recreate the important variables for a given reaction. So nuclear theorists have to spend a lot of time tuning the parameters of their model in order to match experimental data, such as in the plot to the right. This parameter tuning process is called inverse modeling, and it's typically done using statistical methods such as Markov chain Monte Carlo, because we don't just care about the predictions, we also care about the accuracies or the uncertainties associated with them. Now, the problem is that MCMC methods are known to be quite slow, and one reason is because they require many, many evaluations of the forward model, which in this case is computationally expensive, to recreate or to create the inverse model. Next slide. That's where my project this summer comes in. I am using Bayesian GIN, a decision trees initialized neural network paradigm, to create faster approximate forward models. The speed up for one evaluation of my approximate forward model is at least 20 times faster than the exact model. And the additional uncertainty from using an approximate model within an MCMC framework is accounted for by the Bayesian nature of the algorithm. I've integrated this method into a previously existing parameter estimation code and tested it for a zirconium-90 neutron capture reaction. This faster method is now ready to be used for other nuclear reactions involving many of the other 3,500 known isotopes from that first slide. Thank you.
Thanks very much, Kirona. Great job. So what's next for you after this summer?
That's a good question. I guess that I'm hoping to return next summer to continue work on this project. We have a few different ideas on how we can further speed up this MCMC method, including sort of using the same machine learning paradigm to come up with a better initial guess for our models.
Terrific. Thank you so much for joining us today. Great presentation.
Thanks.
Our next speaker is Matthew Durbin. Matthew.
Any radionuclide can be a threat if there's enough of it, but it's not always easy to tell how much there is. So this summer I've been asking, was that a threat? And I've been working on ways to estimate radiological source activity for detectors on the move. My name is Matthew Durbin, and I'm a PhD candidate at Penn State University and a summer intern with the Nuclear and Chemical Sciences Division. Next slide. The overall goal of the project I'm helping to support this summer is really to protect cities from nuclear and radiological threats. This is an intrinsically difficult task as radionuclides can be found everywhere. Radiation is found in the background, in the soil, in the dirt, in the air, in construction materials, and radionuclides are used in various applications in industry and medicine, among other things. And while certain radionuclides are considered a threat due to their association with weapons, really any radionuclide can be a threat if there's enough of it. So not only do we have to detect radiation, we have to distinguish background and benign sources from what could actually be a threat. In order to do that, we need as much context as possible to make informed decisions. So the goal I'm working on this summer is to estimate radionuclide activity to assess threat level. Next slide, please. How we actually go about doing that is by first predicting the DOCA, or distance of closest approach. Once we get a good idea of the DOCA, we can figure out the activity using simple physics and then use the activity to assess threat level. One of the ways we can get an estimate of DOCA is to use a back projection algorithm, shown here to the right. What the back projection algorithm does is it gives us a heat map of signal to noise ratios. The heat map is shown here in the top left, and that pink X represents a hotspot in the signal to noise ratio, or a local maximum. And we can assume that that's going to be the source location. Once we have that, we can get a good idea of the DOCA. We can take this a step further and plug in some of the outputs from our back projection analysis, along with some other features from our contextual sensors available to us, and plug that all into a machine learning analysis. In this case, we used a random forest regressor. Next slide, please. This plot shows some of our preliminary results, where the x-axis represents the signal to noise ratio and the y-axis gives our DOCA error. In purple, we have our simple back projection, and in peach, we have our machine learning corrected back projection. So you can see, especially at low signal to noise ratio, that there's really a good benefit of using the machine learning here. But in any case, throughout the range of signal to noise ratios we're interested in, Both the back projection and random forest gave us really useful DOCA estimates. From here, source activity can now be estimated and combined into a comprehensive threat analysis so we can ask the question, was that a threat, and help keep our cities safer. Thank you.
Thank you very much, Matthew. Great job. We just had a question come in. What is the normal amount of radionuclide activity, and when does it become a threat? How do you avoid false positives?
Right. So like I said, radiation is all around us. So if we take a detector roughly the size of our fist or something like that, we'd get roughly 30 counts of radiation per second, or at least in gamma rays. So really, what would be a threat is when we see many times greater than that. So if we see 32, 33, 34, maybe we're not concerned. If we begin to see 60, double, triple, an order of magnitude more than our normal background, that's when we're going to be concerned. And in regards to false positives, one of the ways we can do that is many of the detectors used, like the one used in this application, has energy information available to us through their gamma ray spectrometers. So we can tell, so there's times when specific isotopes will give us energy signatures, which will be different than typical background. So we can use the energy to flag false positives.
Great, thank you. We have time for one quick follow-up. Is this experimental data or simulated?
So this data I used is from my own simulations, but the overall project does have access to actually lifetime data. Some of these detectors are being used right now as we speak. And so the next step is to incorporate some of this into the existing framework so we can plug this into real data, even potentially lifetime data.
Terrific. And lastly, if you can comment, what is your ultimate career goal, if you're ready to share that? What's next for you?
I'm in my last year of my PhD. So I'm hoping that, I impressed my mentors enough so that they might keep me on for a postdoc in the coming year.
Super. Thank you. Great job, Matthew.
Thank you very much.
Our next speaker is Brian Garcia. And let me pull up Brian. Hi, Brian.
Cool. So enabling the extraction and analysis of data is crucial for discovery in scientific computing. So to that end, this summer I've been working on a new workflow that will allow us to gain greater insight into our AL simulations. So before I go any further though, my name is Brian Garcia. I'm a recent graduate from UC Santa Cruz with a master's in scientific computing and applied mathematics. And this summer I've been working with the Advanced Machine Learning Group here at WCI, and we're excited to share our progress. Next slide. Okay, so our problem resides in the realm of arbitrary Lagrangian Eulerian simulations, or AL sims for short. These are computational codes that are often used to model physical systems in which strong distortions may occur, such as shocks. The thing is, with these AL sims, they're prone to mesh tangles, and these are catastrophic for our simulations. And in order to avoid these, we employ what are called mesh relaxation strategies. And whether these are hand-tuned models or machine learning models, they all monitor certain metrics of the mesh in order to decide whether or not to perform mesh relaxation. That is the act of rearranging the vertices in the cells in order to try to reduce the likelihood of a tangle. Now, with the recent interest and the performance that we've seen out of our machine learning models as mesh relaxation strategies, a question arises, and is how well do our machine learning models generalize across the simulation space? And currently we don't have a tool or workflow in our in-house toolkit to probe this question. So next slide, please. So that has been the focus of my work this summer, and it's to develop this new workflow that will allow us to perform large-scale parameter studies on our machine learning models. So the first step in the workflow is to generate the trained model. And we do this with our in-house tool called VideaAL. We first take a list of simulation parameters and values of interest that we want to test, and we feed it into VideaAL to obtain this these machine learning-based mesh relaxation strategies. So with this model in hand, we can then proceed to step 2, and that is the actual parameter study itself. And we essentially employ another tool called Maestro to generate multiple simulation runs with multiple combinations of parameters to essentially stress test our model to see its performance. After completion of these simulations, we gather them all into a single location that we call a coach store. Now, with this coach store, we can use the underlying coach infrastructure to probe the data sets in order to obtain summary statistics that can be used to further improve our model design. Next slide. Okay, so this is still work that is in development, but this is a very important tool to have in our toolkit since it will allow us to investigate questions of varying complexity, such as how well do our simulations match our experimental data, or even more important in line with our interests, such as how to effectively design these machine learning based mesh relaxation strategies. Thank you.
Great, thank you so much, Brian. Can you speak to anything else that the VideaAL has been used for at the lab?
So it's essentially, as far as I'm aware, VideaAL has been used to generate these mesh relaxation strategies for codes, AL codes called COL, and there's currently other codes that are that we would want to use this for. But that again, like I am not too knowledgeable.
No worries, no worries. Believe me, I'm one of the lesser technical folks in your audience today. And in fact, another question maybe for those of us who are less technical, could you help explain a little more about what a mesh tangle really is?
Yeah, so as this AL simulation evolves, the cells are going to be evolving as well in the computational domain in order to conform to, say, material boundaries or interfaces. But as this progresses, if we don't interfere, a tangle might occur as the mesh evolves. So that is like as we're moving the mesh around, it could very well start to twist on itself.
Got it. Now the questions are starting to roll in, so I have a couple extra minutes if you don't mind.
Sure.
The first is the audience member was thinking that AL models were previously used to switch between a Eulerian and Lagrangian computation to handle the bow ties in the mesh. Is this the VideaAL that you referenced?
Yes. So VideaAL we're operating on these AL codes that could switch between the two. So essentially, we are generating these models to decide when to employ the mesh relaxation.
Okay, great, thanks. If you could, can you sense if there's only a tiny fraction of the bad mesh cells that are controlling the overall simulation?
I believe the infrastructure is in place to do that. There is like it's a very, very complex piece of code that we've put together, but part of the analysis that I perform is operating on files that do indicate which cells are bad cells, if you will.
Got it, thank you. And then the last question we had from the audience, what machine learning technology is underlying this? For example, neural nets, et cetera.
Yeah, so as far as I'm aware, we are performing this deep learning with both a torch, the PyTorch framework, but we are also using our LBAN, which is our LBAN framework, which is our in-house deep learning model, and in-house as in Livermore based. So.
Super. Thank you so much, Brian. I'm sorry we're going to have to move on to our next speaker, but great job.
Awesome. Thank you.
So our next speaker today is Kai Goodman. Welcome, Kai.
Hello. Hi, everyone. My name is Kai Goodman, and I'm based in Fremont, California. I have received my bachelor's degree in material science and engineering from UC Davis, and I will be pursuing my master's degree at Stanford University starting this fall. And my project is on copper dendrites and surface engineering for enhanced CO2 reduction. Next slide, please. So CO2 reduction is the process shown in the top left, where gaseous CO2 is converted using electricity into renewable chemicals and fuels, thus closing the industrial carbon cycle in the effort to offset global CO2 emissions and combat global warming. And looking to the bottom left, we see a typical CO2 reduction reactor, where our electrodes are submerged in aqueous electrolyte and gaseous CO2 is bubbled across the copper catalyst, also doubling as the cathode. At this cathode, gaseous CO2 and protons are reduced to form our hydrocarbons of interest. This process yields many different carbon-based products, shown in the top middle plot, but the products containing multiple carbons, shown in blue, are the most desirable, as they have the highest energy content and market price. Now, the deployment of commercial CO2 reduction technology is currently limited by its low overall efficiency towards CO2 reduction, as well as poor selectivity towards these more valuable products. The goal of this project, as well as my contribution to the work, was to then use various methods of catalyst surface engineering, such as increasing catalyst roughness or using polymer coatings to 1, increase the overall efficiency towards CO2 reduction, and 2, increase the relative selectivity of multi-ordered carbon products. Next slide, please. So in order to execute this goal, we can use electroplating, shown on the left side, to deposit a thin film of copper dendrites to increase the catalyst roughness. By tweaking and optimizing these electroplating parameters, we can control the relative roughness factor, or RF, of each sample compared to a planar copper electrode. Then, shown in the top right, various polymer coating solutions can be applied to the catalyst via drop casting or dip coating to yield unique morphologies and wetting characteristics. And once the catalysts are prepared, they are then loaded into this reactor shown in the bottom right, where CO2 bubbles are incrementally incident on the copper catalyst as shown. When these CO2 reduction parameters are applied, gaseous products evolve off of the catalyst cathode, which can then be sent for product quantification and analysis. Next slide, please. So first, we can observe the effect of roughness factor on the relative ratio between 2 carbon and single carbon products. From these results, we see that the relative selectivity of C2s over C1s increases with roughness factor, where a rougher catalyst exhibits a higher active site surface coverage during a single bubble's incidence, effectively raising the efficiency towards 2 carbon products. Then we can see how various polymer coatings affect CO2 reduction. Here, we compare uncoated copper dendrites with those coated with a hydrophilic polymer, a hydrophobic polymer, and a combination of the two. It can be seen that a hydrophilic coating will increase the availability of protons, while a hydrophobic coating will increase the availability of gaseous CO2. And finally, when all of these methods of surface engineering are combined, we can show a 25-fold increase in the overall efficiency towards CO2 reduction, while also enhancing the selectivity towards multi-ordered carbon products, thus advancing the promise of commercial CO2 reduction and motivating the world to utilize atmospheric CO2. Thank you for your time, and let me know if you have any questions.
Thank you so much, Kai. A very timely project subject matter and presentation. Great job. Question from the audience. How large is the bubble diffuser? And does increasing its size enhance the CO2R reduction performance?
Yes, so the reactor that I've designed here, the catalyst that I'm loading into it is about 1.5 centimeters squared. And this is kind of similar in size and scale to like cutting edge CO2 reduction technology, because if you scale up your electrode size and your reactor size, you introduce a whole bunch of different problems, including like capacitance charging, temperature fluctuations at your catalyst surface, all these things that make scale up very difficult. So cutting edge CO2 reduction technology is usually on this scale of about 1.5 centimeters squared.
Okay, thank you. Has this idea been explored by others that are interested in similar reduction goals?
Yes, this is a, or it's an increasingly studied topic for sure. There's a lot of different methods of tweaking. Like as you can see, there's so many different parameters that you can control, and there's countless studies on each one of those parameters and how they all interplay with each other and how they all affect overall selectivity and overall CO2 reduction product formation.
Great, thank you so much. Great job on your presentation. Appreciate you being here today.
Thank you.
I'm going to move us to our next speaker, who is William Moore.
Right. Hello, everyone. Sorry, that last presentation just had me so excited. Hello, my name is William Moore, and I'm a master's student of material science and engineering from UC Davis. Over this summer, I've been working with Andrew Lang to determine how diffusion during the manufacturing of fiber optic laser preforms affects their final chemistry. Next slide. So fiber optics are long wires of glass that are used to transmit concentrated light, kind of like how power lines transmit electricity. Fiber lasers are lasers made from fiber optics, and they have many important applications in our modern world. For instance, most of us know about the miles of fiber optic wire that connect the internet. But what we often don't think about is the increasing prevalence of fiber lasers in unique and market valuable applications, such as 3D printing. For a long time now, lasers have been imagined as a potential defense tool, and modern high-powered lasers are beginning to turn this science fiction dream into a reality. Lastly, fiber lasers are used close to home in the 2 megajoule laser of the National Ignition Facility. So fiber lasers begin their life as a thick rod of glass known as a preform before they are eventually drawn into the long fibers that we know that are only hundreds of micrometers in diameter. It is the making of these preforms that my work is focused on. Next slide. So fiber laser preforms are doped with a variety of elements in order to tune the optical properties of the final fibers. Typically, fiber laser preforms are made by a process called chemical vapor deposition, CVD, in which gases chemically react and solidify to create glass with the desired chemistry. However, gas deposition only allows for a select few dopant elements. So we here at LLNL use a four-step liquid-based process in order to increase the number of possible dopants to encompass nearly the entire periodic table, making the possibilities for doped core fiber optics nearly limitless. To begin this liquid doping process, you take an open tube of silica glass and then form a layer of porous silica on the interior of this tube. This porous layer is made up of silica nanoparticles created through a Lawrence Livermore developed sol gel process. The tube can then be dip coated in a dopant solution where the porous silica will fill like a sponge with dopant-rich liquid. The tube, finally, this tube is heated and collapsed into the final shape of the preform with a doped silica core and a pure silica shell. My work explores the third step of this process, where I've used COMSOL multiphysics simulations to model the dopant solution as it enters the porous glass and then dries. Next slide. So we begin the simulations by using a detailed model of the porous silica structure to find the fundamental properties of each dopant as they flow through the network of nanoparticles. We can then insert these properties into a larger big picture model to realistically simulate how the dopant will diffuse through the porous glass. If we know how the dopant will travel, we can predict the final composition of the preformed cores. And as we know from the most basic mantra of material science, composition controls everything. Powerful simulation tools like COMSOL allow us to preview these complex manufacturing methods and understand their strengths as well as their limitations, such that no new breakthrough in the creation of laser optics is beyond our reach. Thank you very much.
Thank you so much, William. I continue to be amazed that all of you performed this incredible research this summer remotely without even getting to be at the lab physically. So really great job. One question you mentioned at the beginning of your presentation about 3D printing. Can you share more about how fiber lasers might be used for 3D printing?
Oh yeah, so 3D printing for things like metals, so metals, you don't exactly just lay down the metal as molten metal. You have to essentially lay down a powder of metal, and then you fire a really high powered laser at that metal to melt it and resolidify it. And so fiber lasers are a way of generating a laser that you can fire out of the laser. You essentially generate the laser inside the fiber optic, which is awesome because you can also direct the laser using the fiber optic. And so then you use this laser created through fiber lasers in order to melt the powder bed of the metal and essentially build up layer by layer your 3D printed object.
Got it. Thank you so much. That was helpful. We had another question from the audience wondering if you have compared your simulation with the experimental data.
Right. Okay. So what I'm doing this for is in order to test. There was an issue with the composition profile of these cores. So like you imagine, it's a cylinder. And the problem we were having is at the center of these cylinders, there was a drop in the concentration. And so what I've been doing with these simulations is trying to get a sense of how dopant diffuses, how quickly it does, and eventually how it will behave when it dries. I have not been able to compare with any sort of experiment because we are currently in a stage of developing the detailed structure. We're expanding it from more than just this 2D picture I have here into more of a 3D network of particles where we can get some important information to describe diffusion within the glass. There's multiple steps to this process. Unfortunately, I don't have any data to compare this to. I think it's fairly reliable considering the information that we're getting can be compared to other porous situations, because we're for the most part looking at these things called porosity and tortuosity, which you can compare fairly easily.
Got it. Thank you so much for a fantastic explanation and presentation. I'm going to move us along, but we appreciate your time, William. Thank you.
Okay, thank you.
Our next speaker is Henry. Welcome, Henry.
Hi, can you hear me?
Yes,
Hello?
we can.
Okay, perfect. Hello, everybody. I'm Henry, and I'm a fourth-year PhD student studying optical sciences at the University of Arizona. My mentors this summer were Stacy Manuel and Sid Pedinkar, and I had the amazing opportunity to track down ghosts with them. Next slide, please. So what are ghosts? Ghosts are extra reflected images which find their way to a target, such as your eye or a camera sensor. You can see that the light from an object that strikes this blast window both transmits through and reflects at the interface. When extra reflections, shown in the red arrows, happen twice, similar copies of this image are sent to the target even when we weren't expecting them. For even numbers of reflections, we'll get second-order ghosts, fourth-order ghosts, and so on, growing fainter with every generation. As for a real-life example, ghosting is happening inside these pair of eyeglasses below my office lights. There's actually only 2 lights above me, but the number of lights we see in each lens has ballooned because of surface interreflection. Even for a simple system, you can see that separating ghosts from the true image can be really difficult. But when you put prisms, lenses, and beam splitters in the path of a high-power laser, you can generate families of thousands of ghosts, which can blind cameras and even damage optics. Next slide, please. My mission this summer was to investigate the ghosts and stray light inside OTSL, or the Optical Thompson Scattering Laser. The OTSL is a 1 gigawatt laser that uses 5 omega or 210 nanometer light to examine the plasma generated by every whole ROM shot. If you follow the bold black arrows in this ray trace, you'll follow the main path that the 5 omega light nominally takes to get to the TCC, or target chamber center, and also the alignment camera. Unfortunately, this isn't the only path the light can take through the system, because 1, we know that ghosts can be generated by multiple reflection, and 2, we've seen ghosts at the detector experimentally. To diagnose these ghosts and begin eliminating them, I used an optical analysis software called FRED, which traces millions of rays through an optical system and lets us peer into where these ghosts may have come to life. You can see in the lower 3 figures that light can converge, diverge, and refract in so many unintuitive distributions. I know this ray trace looks scary at first, but as scientists and engineers, we can untangle this massive web of possibilities. We trace millions of rays, isolate the most interesting paths, and interrogate them. For example, at lens L4 in the 4th figure, you can see that light skirts the aperture and creates 4 straight beams. And in the final figure, this same ghost path stands out at the busy detector plane. Final slide, please. Here's a comparison between a camera image taken in April and what the true design signal is supposed to look like. During my ghost interrogation, I trimmed off families of ghosts that were too faint to compete with the true beam. I applied real manufacturer test data, calculated artifact magnification, and incorporated the anecdotes of the OTSL alignment team. From this work, I've generated a taxonomy of ghosts, some of which are plausible and sometimes even fun spatial patterns like bow tie, wisdom, and toast. Some of the ghosts don't fully match what we've been trying to track down yet, but the work I've done this summer shows that 1, we can narrow down the wavelength sources of our ghosts. 2, there's a possible point-like source in the vicinity of the whole ROM. And 3, we need to watch out for background source ghosts as NIF scales to higher power. In high power lasers, ghosts often exist, but at LINS, we have the capability to diagnose their origins and maximize the performance of our instruments. Thank you for your attention. Thank you to the brilliant and amazing OTSL team, and be ready for future episodes of NIF Ghostbusters. I'll take any questions.
Thank you so much, Henry, and extra points for a great project title for those Harry Potter fans out there. A couple of questions for you have come in. What was your favorite ghost to track down, and which one had the biggest fight?
So ghost hunting is really weird because you find these ghosts by tracing millions of rays, and you see what happens at the detector, and you kind of have to dismiss them on a case-by-case basis. The very last one looks I call it the conch, and that was really interesting, but it's from different, it was a different harmonic, like instead of the 210 nanometers, it was at the second or third harmonic. Bow tie ghost was actually one of the funnest ones I found because initially I dismissed it and thought it was just a red herring, right? Not in shape, but the bow tie ghost is actually just a defocused beam that was clipped by a square aperture. And so that ended up being a spot on ghost that some of our alignment people found in the system. And that was probably the greatest moment I had all summer. So yeah, maybe bow tie ghost would be my favorite.
Super, thank you. A couple of folks are interested in how you mitigate the ghosts, and one in particular suggested, could you use special coatings on the mirror to control the number and intensity of the ghosts?
That's a fantastic question. So one of the big problems with high power lasers is that the coatings and the optics can't handle that much power. Some bandpass filters, some anti-reflective coatings can only handle so much power, so we're kind of limited in what we can attenuate at specific locations and optics that guide the light through the system. You can use specific absorptive filters for very low powered light. In my system, we have a lot less power by the time we hit the camera, so we possibly might consider some absorptive coatings, but for high power lasers, we want to reflect the light out and scatter it to be as diffuse as possible so that the energy is more spread out. Usually we'll try to deflect the light more than just try to take in and absorb it at a beam dump. I hope that answered your question.
Yes, thanks so much. So what's next for you, Henry? How will you be building on this work from the summer?
Right now I'm finishing up the last week of my internship, so I'm making recommendations, having as many conversations as possible with our alignment team. And yeah, just closing out with great documentation. That's the plan.
Terrific. Well, we're happy to have you this summer at the lab, Henry. Thanks for your presentation.
Thank you.
Our next speaker is Elizabeth Reed. Welcome, Elizabeth.
Hello, thank you. Happy to be here this afternoon. Today I'm going to talk about how we are investigating new techniques to improve the resilience of the energy grid. My name is Elizabeth Reed, and I'm a graduate student in electrical and computer engineering at the University of Illinois at Urbana-Champaign. This summer, I've been working on part of a larger project that strives to utilize deep reinforcement learning to train a defender agent to protect against disruptions to the grid. And specifically, I have been focusing on how we can use data from real systems to improve our simulation environment to accurately reflect device behaviors. Next slide, please. Defending the power grid is a national security priority, and this is the primary motivation for our project. The operation of these systems is critical, and they have been targets for a range of cyber attacks, as has been observed in a number of news articles and reports. As attackers continue to target these high priority systems, we also need to keep investigating strategies to protect these systems from disruption. Next slide, please. Our approach for improving energy grid resilience involves modeling the components of the power system and using deep reinforcement learning to allow an attacker agent and defender agent to observe the environment and take corresponding malicious or defensive actions on the system. We would like to expand this model by not only including the underlying electrical components, but also the cyber physical components involved in the operations technology, or OT aspect of the power grid. In order to gain a better understanding of these components and their actions in the grid, we have been looking at detailed data sets from multiple sources that have been provided by power engineers from Site 300 at Lawrence Livermore National Lab, and from public PG&E sample feeder data. By observing the topological data of the lines and devices in Site 300, relative patterns in this data help guide placement of OT devices on synthetic systems and in system models with incomplete data. Next slide, please. In addition, PCAP files from Site 300, which consist of network traffic packet data that has been sniffed from a single point in the network, were analyzed to obtain information about the normal communication behavior of the devices in the system. Behavioral communication features abstracted from this PCAP data help describe potential configurations for simulated OT components in our model, such as reporting frequencies. Given the knowledge of the specific OT device models present in the system, I've also been able to investigate the capabilities of these devices to define lists of potential actions for these components, which would be utilized by the defender agent or by an attacker agent that has compromised the device. For example, if an attacker compromises a specific protective relay, that would limit the attacker to opening and closing that relay alone. In contrast, compromising a particular RTAC or real-time automation controller device would allow an attacker to potentially send malicious commands to all the protective relays connected to that specific RTAC unit. Integrating these features to our existing environment model and software and adding this OT device layer to the environment will provide new options for configuring the actions of a directed attacker agent and will help us develop new strategies to defend against cyber attacks to the power grid. Thank you.
Thanks very much, Elizabeth. Great presentation. And again, very timely subject matter. Wondering, and we have a couple questions that just came in and I had one too. Is there another way of saying this, that you're using artificial intelligence to determine abnormal power grid behavior and discover a hostile attack?
Yes, we are using basically this deep reinforcement learning, an agent basically to both recognize that there is a problem, and this could be an attack or it could be like a disruption to the grid, like a natural disruption as well. And the purpose is for the defender agent to respond and basically restore power to the grid. Yes.
Thank you. And a quick follow-up, could the network elements be made smarter or provide additional information to help defend the network?
So we are trying to basically utilize what is, one second, let me answer this. So basically, we are looking at modeling what is available within the system. So there are components in the system which are smart, and we want to recognize, basically employ the potential action space of those components to respond to disruptions. Mm-hmm. If potentially moving forward, devices are enabled to basically have more action spaces, then yes, we would like to reflect that as well.
Thank you. Okay, another question has come in. How do you find intermittent malicious communications?
So in the scope of our project, we are looking at actions that directly have basically a big impact on the grid. And so we don't highlight intermittent malicious communications until they cause a disruption. Mm. Moving forward, that would be an interesting space to look at, to be able to identify that kind of malicious communication before it has the impact. But currently we're looking at only the direct impact right now.
Great. Thank you so much, Elizabeth, for your presentation today. We appreciate it.
Thank you.
Our next speaker today is Payal. Welcome. Payal, you worked with computing this summer. Nice to have you here.
Yeah, hi. Thank you for coming, everyone. My name is Payal Singh. I'm currently a graduate student in electrical and computer engineering at UC San Diego. And this summer, I worked in NIF automatic alignment on increasing the speed of the current position detection algorithms using Python and sub-imaging. Next slide, please. So just to provide some background on the NIF automatic alignment, there are thousands of digital cameras throughout NIF that are used to detect the beam positions of the 192 laser beams. And the NIF automated alignment system consists of image analysis codes that are written in a language called IDL and motorized mirror-based feedback control loops that ensure that the beams are precisely aligned to that millimeter-sized target. And so these algorithms must be robust to different illumination conditions, aging, and eventual replacement of components, and even more. And so these different conditions that I just mentioned, they return different noise characteristics in the alignment images. And so given these, when the beam position is returned, the algorithms must also tell how confident we are in the position accuracy. So the automated alignment systems uses fiducials, some of which I have pictured here, that are imprinted on the beam to indicate the beam positions. Some of which are, you can see here, are circles, squares, or lines. The results of the sub-imaging that I'll be presenting about are actually about finding the center of this small pinhole in the middle here. Next slide, please. So in the title of this presentation, I mentioned Python and I mentioned sub-imaging. And so the rationale for wanting to try Python over IDL for this project, which is the language that the code is currently written in, is that the speed of certain basic operations that are commonly used in image processing codes. So for example, matrix copy and FFT, they're slightly faster in Python than IDL. Also, Python code can be optimized to be even faster by using compilers such as Numba and Cython. The rationale for introducing the sub-imaging is also clear. It will result in an increase in processing speed since you would be performing operations on only a small part of the image rather than the entire thing. And additionally, actually, the alignment loops for extra accuracy, they may be converted from the nominal 480 by 640 pixel size to a full camera size, which will obviously increase the processing time for many of the loops. And therefore, having a sub-imaging will cut down on that extra processing time. Next slide, please. All right, and I have some preliminary results here for sub-imaging speed in Python using a 100 by 100 pixel sub-image size. And so these columns are different sizes of image, and the rows are the types of sub-imaging that are done. So for example, the first row is running my algorithm on the full image size as indicated in the column headers, and the other rows are various types of sub-imaging, meaning so no overlap, certain amounts of overlap, and then using a priori information about where the pinhole center is. So you can just hone in on a sub-image exactly where the pinhole is. And there are a lot of numbers here, but I'm basically trying to show that for different image sizes, the sub-imaging is faster than performing operations on the entire image. So some future work for this project is to make the sub-imaging grid and algorithm that I'm using more robust and apply the sub-imaging to, for example, a diffraction ring detection used in the optical Thompson scattering laser image processing to substantially reduce the optimization time. And that's all I have. Thank you very much. I can take any questions.
Thanks very much, Pyle. One question we had was, is this type of automated alignment used in other industries or for other applications?
I wouldn't be surprised if it was. The one that I'm most familiar with, obviously, is the NIF, because you have the 192 lasers and you're trying to align them precisely to be exactly where you want them on the whole ROM. But yeah, I wouldn't be surprised if this sort of technique was used elsewhere.
Great, thank you. Another question, are those numbers for standard Python?
Yes.
Okay. Terrific. And what's next for you, Pyle? I know you've identified some areas for future work, but what about you personally?
So I still have a little bit left to go. I'm currently a master's student at UC San Diego. So I'll, like one of the other presenters said before me, hopefully I've impressed my mentors enough, they'll invite me to come back.
Great. Well, you're off to a great start, Pyle. Thank you so much for your presentation today.
Thank you very much.
Our next speaker is Rebecca Wheeler. Welcome, Rebecca.
Hi, thank you very much. So I'm actually going to kind of pick up where Pyle left off at where our lasers are hitting. My name is Rebecca Wheeler. I am an undergraduate student at UC San Diego, and today I'm going to explain to you why diamonds are the NIF's best friend. Next slide, please. So as Pyle was saying, we're shooting a target with many lasers, right? So where I come in is with the capsule. We're shooting this target and we're heating up a Hall ROM enough to actually implode the fuel that's inside the capsule. So our capsule has to be practically perfect in order to get the best possible explosion and the best possible yield. Knowing every little thing about this capsule is very important in determining the pulse size and power for our lasers. So this is where I come in. I've been looking at the density of our capsules so that we can very accurately decide what laser peak power we want. Next slide, please. Next slide, please. Okay, thank you. So you may think it's pretty simple to take the density of our capsules. However, it's not the case. We think of it as mass over volume, but we cannot get a volume for our capsule with enough certainty for the NIF's very stringent specs. So what we end up using is the ancient Archimedes principle in a very modern application. we have to mass our capsule in air and take the apparent mass of our capsule in liquid where a net buoyant force works on it. And using these two measurements and Archimedes' principle, we're able to get the very elegant equation that you see at the bottom of your screen that allows us to use the very accurate and precise microbalances that we have at our lab in order to find a very precise measure for our density for the specs that NIF needs. It's so precise that we're even using the density of air in our calculations. We're not just assuming that it's 1. Next slide, please. So now that we have our density measurements, it's really interesting to look at the trends that we see within our density in terms of how our capsules are grown and how they will perform. We can grow our capsules in 2 main crystalline structures through our chemical vapor deposition plasma-assisted process. We can grow microcrystalline capsules, which are a larger crystal structure, and nanocrystalline capsules, which are essentially amorphous crystals. Microcrystalline capsules actually act the way that we would expect them to act with density. So we dope our capsules with tungsten, a higher Z particle, which is going to increase the density because it is a higher density than the high density carbon diamond that we were using before. So when we dope our microcrystalline capsules with tungsten, we actually do see our linear increase in density as we would expect. However, on our nanocrystalline capsules, we don't see this linear increase in density when we're adding tungsten. We actually see a decrease in density up until a critical concentration, at which point we do once again see our increase in density. Why might this be happening? Well, we don't know for certain, but we do have a hypothesis that we are in the process of testing for this nonlinear density behavior. We believe that along the many grain boundaries in our nanocrystalline capsules, we're actually getting the formation of sp2 hybridized carbon or graphite, which has a much lower density than the tungsten and would therefore explain our decrease of density with the increase of tungsten. We don't know if this is the case, but as I said, we are in the process of testing it. And understanding our diamond capsule density and the materials that go inside of them could be the next step in helping to bring the stars to Earth. I wanted to thank our wonderful HDC team, as well as all of you for being here. I can now take any questions.
Thank you so much, Rebecca. Great job and great project title. Again, you all are being very creative in capturing audience attention. You touched on this briefly, but how could you continue to build on this research? How much more is actually needed to begin growing and using these types of capsules for NIF?
We have been using these types of capsules. We buy them from Diamond Materials. And what we're doing at the lab currently with these capsules is we're experimentally determining the best possible parameters, which is where this research kind of comes in. The next steps that we're taking directly from these density measurements is we're using Raman spectroscopy to try and figure out the concentration of graphite or the relative concentration of graphite between different capsules. So that's where we're starting at this point.
Got it, thank you. And what's next for you? Are you wrapping up your internship as well?
Yes, I'm actually going till September, which is I'm very excited about. And then it's back to school.
Terrific. Well, we're happy to have you here today. Thank you, Rebecca.
Thank you very much.
So our next speaker is Randy. He's actually our final speaker of the day. I'm going to stop sharing my screen briefly so that Randy can share his. So I will hand you the stage, Randy.
Thank you. I will share right now. Oops. Can everyone see my screen?
Yes.
Okay, sorry. Trying to move it back. Sorry, let me try that again. Okay, so my name is Randy Posada. I'm from the University of California, Merced, and I am a biological sciences major, and my emphasis is in human biology. I'm an incoming 4th year, and I am from Joshua Tree, California. So my LLNL project is drug safety, target identification, and future applications to COVID-19 drug discovery research. My mentor is Mary Silva. So I'll be presenting today an organized approach to drug safety, and a brief shout out to the amazing drug target ID team and the UCSF Spoke investigative team. So the data used in this study comes from the Spoke database. Spoke stands for Scalable Precision Medicine-Oriented Knowledge Engine. It's a database of databases provided by the University of California, San Francisco. The graph theoretic database allows researchers to explore interconnected pathways, and it is immensely large and contains more than 2 million compounds. The data from Spoke is held by Neo4j. Now, Neo4j is an approach to database design that provides flexible schemas for data storage and retrieval. It's a querying language like SQL, yet it contains spatial relationships such as nodes and edges, which interest us when analyzing the Spoke data. So as our visualization tool, Neo4j stems beyond the traditional table structure that we find in relational databases, and we can access the data through queries which produce an appealing result, such as this one. Now, here we ran a query for the compound acetaminophen, which is Tylenol's only active ingredient. We were able to see the proteins, side effects, and diseases that were connected to this compound. Now, we want to apply mathematical modeling, statistical inference, and featurization in order to make predictions. The aim is that these predictions will eventually facilitate the screening for compounds and drug synthesis using data science. Now, since liver toxicity is an utmost importance when screening for compounds, we conducted a binary classification of DILI, no DILI. Now, DILI stands for drug-induced liver injury. As you can see, acetaminophen is a DILI concern. On the warning label, they even state a liver warning. In this classification, the compounds that cause injury to the liver are assigned to 1, while the compounds that do not cause an injury to the liver are assigned to 0. Now, from here, we can featurize our data. This is a graphical representation of a small portion of the Spoke database. These queries take a very long time to run due to the size of the data. This is why we randomly sampled 400 compounds that were equally DILI, no DILI. Now, from these 400 compounds, we used 80% of them to train the model and 20% of them to test the model. Here's a tabular view of our featurized Spoke data. We can see the values for each of the given compounds, and they all have unique chemical ID names. These chemical ID names come from a chemical database. Now, the first compound here in the red arrow is actually acetaminophen from the previous slide. And as you can see in the response column, there's a 1, indicating indeed there is a liver injury concern. Now, max phase is the phase of clinical trial it is on. The proportion of liver anatomy is the proportion of anatomies that are connected to the compound. And the proportion of safety proteins is the proportion of compound experimental binding proteins that may indicate potential drug safety issues or toxic effects. Now, these two last columns are categorical. We ran a featurization for both categories using the word hep for hepatic and liver. Now, the compounds that cause any related side effect or diseases pertaining to the liver can be classified as liver-related or non-liver related. For the sake of time, now let's take a look at the obtained results. Now, the overall goal of the project was to build a simpler classification models that we can use as benchmarks for larger graphical models in the future. We want to know, do these models outperform our benchmark? We also set this up as a software pipeline for reproducibility. And we want to easily be able to change the parameters later on, such as the hyperparameters of the random forest and the neural network. Now, in the study, we used 3 models to see which one could provide us with the best accuracy. As I said before, we want to obtain a really well-performing model as our benchmark. Now, we used a logistic regression model, a multi-layer perceptron, which is our neural network, and a random forest classifier. The random forest model gave us the highest predicted accuracy at an amazing 84%. So in our conducted RFC curve analysis here, we look for the largest AUC, which is area under the curve. And as we can see by the blue line here, the random forest classifier outperforms all the other models with the largest AUC of 92%. So we decided to use software to run a quick random forest feature importance algorithm, which allowed me to realize that the proportion of the liver anatomies was the most important and had the largest influence on our models. Here in the confusion matrix, we're able to see the model's performance. So whether the model is correctly predicting if the compound indeed causes DILI or if it incorrectly predicts DILI. Now, the model gave a true label here, true label 0, when it was actually 0 correctly 43.75% of the time. And for the false positive, for the false negative, we want it to be as low as possible, since we don't want to give a label of no injury to a compound that indeed does cause injury. Now, in future work, I plan to use these models as benchmarks for other studies, and a goal would be eventually to apply this to all of Spoke rather than just a sample of the data. I would like to classify other compounds also and apply these methods to COVID-19 research for the purpose of target identification. Now, though this study did focus on the liver, we know that heart and liver toxicity are of high importance when screening for compounds. Therefore, my future work will most likely include classifying these heart side effects. And if you would like to contact me to discuss the methods any further, feel free to contact me. Thank you.
Thank you very much, Randy. Really exciting research you've been working on this summer. I know through your fellowship with UC Merced and the lab, will you be continuing this work throughout your senior year?
Yes, I will. I remain here on part-time all the way till I graduate.
Terrific. And have you given some thought to your future plans after graduation?
Yes, I am between applying to vet school and also I've been discussing with my mentor future applications in the lab. So maybe that could be a possibility.
Terrific. Well, thank you so much for your presentation. I'm glad we were able to get the technical difficulties worked out.
Yeah, thank you. Sorry about that.
Thank you. At this time, I'd like to invite all of the students back to turn your cameras back on for a couple of minutes in case we have any final questions from the audience. We have about 10 minutes remaining. And for folks in the audience, this is your chance to ask any other questions, burning questions you might have for the future generation of scientists and engineers, both at the lab and beyond. One question I had, I alluded to it earlier, was just generally, and folks can jump in, what your experience was like this summer engaging with the lab. I know there are unique challenges to remote engagement, but I think being the second summer the lab has done this, they've found lots of creative ways to maintain those connections and communications. If anyone has any comments, observations, what worked well, what was surprising or challenging, feel free to raise your hand or jump in. I think everyone's muted. Don't be shy. Matthew?
I could mention something.
Okay, we'll go Randy and then Matthew.
I definitely got a great experience, more than I bargained for sure. And I was paired with a perfect research group that aligned with my interests, and I have an amazing mentor. And I've been able to really learn a lot, especially in Python, which I wasn't as confident in.
Terrific, thank you. Matthew, did you have something, and then William?
Yeah, so I'd just like to say that, a lot of these programs, 8 to 12 weeks, and you're coming into, pretty large scale projects. So you figure, okay, what can we actually get done in 8 to 12 weeks? Well, with the mentors I've directly interacted with and others I've heard about, there's a lot of behind the scenes works that took place before we even arrived virtually. So that, day one maybe we're in orientation or something like that, but day 2, day 3, we can actually get our hands on real data, real models, so that we can actually hit the ground running and make it really productive, relatively short time.
Thank you. William, did you want to add to that? We have a question from the audience too.
Oh yeah, I just wanted to say really quickly, shout out, what are they called? I think they're called the LLESA. They're a group and they put on a bunch of social events for the students, and they've been doing a really good job. I think the one thing that surprised me most coming into this was how many opportunities to meet other people they were, and it wasn't just me with my head down making a simulation on my computer. I got to meet people, I got to go to events, and I got to go to like seminars and learn a lot of stuff. So great job, everybody. It's been so much fun.
That's fantastic feedback. Thank you, William. I know one of the lab's biggest goals was to maintain a real research community among the students in the summer, despite all of those challenges. So it's great to hear that. A related question that came in was about whether in your projects, if there was something specific that you might have been able to do better or would have been more interesting had you been able to be at the lab in person. Sarah, you're raising your hand.
Yeah, I can talk about this because my mentor, Dean Rusby, he's actually involved in actual NIF shots. So like this morning when we got to see kind of the presentation of the new information, my mentor gets to like be there and like help with all of that. So I definitely think that like I'm looking into full time at the lab, like that's something that I'm really excited for, is like potentially seeing that instead of just simulating it.
Terrific, thank you. Anyone else want to add? Henry?
Sorry. Yeah, I can add on to that. I would say that, you know, there's a lot of cultural aspects to a workplace or a place you want to contribute to or a mission you want to contribute to that seems like you can only emulate that in person. But Lynn's did a really good job at inculcating that into us this summer. They put a lot of efforts into giving seminars, having us meet and rotate and mix with other interns from different directorates. And the mentors were kind of in on it too. Are you doing okay? This is virtual. This is not normal, right? So I would say the only improvement you could have is if you could allow us to peek our heads into NIF, right? But of course we can't be there. Otherwise, giving us the culture that is, you know, that you would like to see and find out more about before you work somewhere full time. That was done excellently over the summer internship.
Terrific, thank you, Henry. Matthew, did you have something you were going to add?
Yeah, so I definitely agree with everything that's been said, but with a slightly different angle, I think the virtual format actually allowed for some opportunities for people to be involved that otherwise wouldn't be. So for example, I'm coming in from Pennsylvania. You know, I have a lease locked in, so on and so forth. So for either logistical or personal reasons, it may not have made sense for me to transfer across the country for 2 months and then come right back. But this virtual format, you know, allows that to be done for not just me, but I know other people were in a similar situation.
Good point. And Joanna had a note in the chat, if folks saw, to make sure there is a virtual NIF tour online. If you haven't had a chance to check it out, I'd encourage you to do so for sure. Any final comments or questions for this? You guys were really impressive and we're so thrilled to be able to bring this opportunity to the community, and thank you for your time. I know many of you are all across the country in different time zones, in different areas. So it looks like Kai has a comment. Sorry, Kai.
Oh yeah, I just wanted to say before we move on from the kind of remote work that I had, I think, a pretty unique experience in that I may, if I'm recalling correctly, I think I was the only one here that was on site for the entirety of my internship. Oh, and Rebecca Wheeler. Okay, yeah. But yeah, I just want to say that I think Lawrence Livermore has done a fantastic job managing all the COVID protocols and, you know, taking everything seriously and considering the safety above all else of the employees. And yeah, I just want to say thank you to Lawrence Livermore for really handling everything expertly.
I have a quick comment to add on. I know that a lot of work goes behind the scenes, so thank you to all the mentors, and also thank you to ULLF for hosting this amazing event for us.
Thank you, Rebecca. That's very kind. I think we've got Donna Crawford back on in case, Donna, you wanted to make any final comments. Again, board chair of the foundation. She's beaming. These are her favorite types of events.
Absolutely. Well, you said it all. I love the presentations. Thank you to our attendees. I hope you enjoyed it as much as I did. And I hope to see many of you back here next year in person. So thank you very much.
Thank you, Donna. With that, I guess we'll wrap up a couple of minutes early. On behalf of the Livermore Lab Foundation and Livermore Lab and all of our students, thank you for joining us today for Summer Slam Special Edition. We hope to see you all next year. As Donna said, fingers crossed in person. But if not, please stay in touch with the foundation's activities on our website, livermorelabfoundation.org, and enjoy your day. Thanks, everybody. And if students can stay on for one more moment after the webinar, we'd appreciate it. Have a good day.
Bye. Thanks, everybody.